this table last week, whereby you want to do the hypothetical path, you need this table. And one thing that I need to point out to you guys is this: when it is an ideal gas, the changes in the enthalpy and the internal pressure is always zero. So you need to look at your conditions. Can you assume an ideal gas? If the temperature is not in the negative, if your pressure is not too high, then you can say that it is, you can assume an ideal gas. Okay? What's going on? Who's chatting? Anything that I need to know? Anything? Okay, no. Okay, so another thing that we need to remember, the change in enthalpy is always the integration of heat capacity with respect to temperature. It's the same thing for liquid and vapor, except that you have this term, you have that volumetric volume timed by the difference in the pressure. But you still have the integration of Cp with respect to temperature. Okay, so same thing with internal energy. You have the integration, same thing over here. Now let's see for liquid and solid, and ideal gas is the same for internal energy. Okay, but it's not the same for ideal gas. For ideal gas, it's not the same. Let me use a different color. Ideal gas is not the same. You have this extra term over here. Okay, that we have done that. Look at it. We have done this last week. We have done a few examples. Now I need to point this out. When you have an ideal gas, the relationship between Cp and Cv, Cp is at a constant pressure, Cv is at a constant volume. The equation is here, Cp is equal to Cv plus R. Your R is your gas constant. But for liquid and solid, the value is approximately the same. Your Cp is approximately your Cv. So whenever it's a gas, how to remember? Easy enough. Gas, normally we have the ideal gas. This is the ideal gas. So you have the ideal gas constant there. Okay? For liquid and gas and solid, Cp is approximately the same. Cp and Cv, constant pressure. Okay, constant pressure is equal to the heat capacity at constant volume. So it's approximately the same. But if it's ideal gas, you have to add in the ideal gas constant. So that's what you need to know. Okay? That's an additional information. Okay, now this is the polynomial equation that you can get from Appendix B2. Right now I'm reviewing what we have done. This is something new. This is for today. Whenever you have a mixture, this is a mixture. Whenever you need to find the Cp of a mixture, normally this is for an ideal gas. You can use this equation. For an ideal gas, you can use this equation. You sum up based on the mole fraction and the Cp of the pure component. Example, you have ethane. What is the value of the H? If it's ethane, is it 6? Is it 6? Guys? Anybody respond, please? Hello, am I speaking to myself? Guys? Anybody? Are you with me? Excuse me, am I speaking to myself? Oh my God.
Yes, we are here.
Sorry?
Yes, we are here.
Yeah, it's 6. H6. Thank you. At least somebody respond. Okay, for example, you have ethane. The value of the mole fraction for ethane is equal to 0.4. For example, just give an example. And the value of propane, the mole fraction of propane in this mixture is equals to 0.6. So what you have to do is you multiply that Y with the Cp of your ethane. which you can get from appendix B2. And your sum it up with that of your propane and the CP of your propane, which you can get from the appendix B2 from the appendix. So this value you can get from B table B2. Yeah. The mole fraction, you multiply it and then you sum it up for both components. So what you have to do for this example, CP of mixture of ethane and propane is equals to 0.4 times by CP of ethane. Okay, that's one. Plus the CP, plus the mole fraction of propane, 0.6 times by CP of propane. Then you will get the CP of the mixture. Alright, so that's how you do it. Any questions so far? Guys, no question?
No question also so far.
Thank you. Okay, now. You can also estimate the CP, but this I just mentioned in passing. There's the COPS rule when you want to estimate CP. For example, you have calcium hydroxide. So you find C. There's C. So how many C do you have? 1. But this is not C. This is calcium. Where is calcium? This is calcium 26 Ca. Is it others? This other, not carbon. Sorry. Let me erase this. Make mistake there. Okay, you have calcium. Calcium is not listed here, so it become others. So that is C. So Ca, that's equal to 26. You have oxygen. You have oxygen there. So oxygen, you have 17. So oxygen equals to 17. And then oxygen, you have hydrogen. Hydrogen is 7.9.6. So remember there's the 2 there. So you need to multiply by 2. And also there's the 2 there. You need to multiply by 2. So you sum it up. Then you will get the heat capacity of your calcium hydroxide. If you don't have any polynomial equation from appendix B2, this is what you have to do. You look up table B10 based on the formula of that component, the equation of that component, you can estimate. Remember, this is an estimation. You can estimate its heat capacity, but it's specifically for solid and liquid, and the temperature is roughly somewhere near 20 degrees C. Okay? That's what you have to do using Cope's rule. Okay? You can estimate for solid and liquid, but not for gases. Okay? So that's Cope's rule that you can use appendix B10, depending on how the equation of that component. Okay, it's based on the atomic heat capacity. So that's one that we're going to cover today. Now, I did mention about table B2. Remember, you have this equation for equation number 1. Sorry, let me undo that. I want to use the marker. This is equation 1. And the other one is equation 2. They are completely different. 1 and 2 is not the same. Right? So you cannot use the same formula if you're looking at equation 2. So for example, where is 2? This is 2. Right? You need to use equation 2. If you're looking at equation 1, then that's equation 1. Then you'll be using equation 1. Okay? So be careful. Another thing that you need to take note of is the temperature. Either you're using Kelvin or using degree C. Both of that you need to take note of. I did mention that. So that's just a brief reminder. And now, this example. This is one example whereby you have carbon monoxide. The CP is given, but you need to find the CP at constant volume. So that CP should be not CP, but CV. Not CP, but CV. So what you have to do is, carbon monoxide is a gas. So you're going to use this formula, Cp equals to Cv plus R. And you bring over the Cv to the left-hand side and bring over the Cp to the right-hand side. So what happened here? Sorry, I did that wrongly. What I need to do is I bring over the gas constant to that side. Yeah, I bring the gas constant, so Cv equals to Cp minus R. Okay, let me use, sorry. I need to look at my example for heat capacity here. The same thing, it's the same thing. It's the same thing. Okay, it's the same thing. So now you have that Cp. Look at the unit, calorie, mole, degrees, degrees C. What gas constant should we use, guys? What gas constant should we use? Anybody? Anybody? What gas constant should we use? You have your appendix at the back, your gas constant at the back of the textbook, at the cover of the textbook.
1.987.
Okay, thank you. Your gas constant should have the same unit as your CP. So your gas constant, if you look at the back of the cover of your textbook, back cover, it's written having a unit of calcium, calorie per mole per Kelvin is 1.987. That is calorie per mole Kelvin. Okay, thank you. At least somebody respond. That's 1.987. So if you write that equation, 6.890, that's 6.890 over here, plus 0.001436 temperature minus 1.987. So this part will be deducted from that. So you will end up with, if you do the calculation, let me get my calculator, 6.89 minus 1.987, you end up with 4.903 plus 0.001436 temperature. So that is the CV, your heat capacity at constant volume. So if you need to find the internal energy, the change in internal energy, this is what you have to use. Internal energy, letter U, the change of temperature from T1 to T2 is always CV with respect to temperature. So if you need to get that value, this is how you do it for a gas. Any question? This is an example.
Doctor,
Yes.
I have a question.
Yes.
The unit for CP is per mole degree Celsius, but for the mole Kelvin, right?
Yes.
So we just minus the R.
Why? Because this is degree C. Sorry, let me use a red color. Yeah, this is degree C. This is degree K. Okay, now whenever you do integration, what you do is actually you get the difference, right? T1 minus T2 minus T1, isn't it? Isn't it? This is what you do, isn't it?
Yes.
Okay, if it's T to the power of 2, then it is T2 squared minus T1 squared, isn't it? Normally, that's what you do when you do integration. So what happened over here is, let me erase this. Okay. Normally, it's all about different. So whenever it's a different, the temperature, whether it's in degree C or whether it's in Kelvin, it will come up to the same value. Because it's a different. Oops, I erased that. Oh dear. Okay. Does that answer your question? No? Okay. It doesn't matter because if this is degree C, yeah, I'm going to erase that. Yeah. If it's degree C, whenever you do integration, you will always use the same, it's going to be the same as the Kelvin. It's still the same. Because it's a temperature different. It's a temperature different. For example, let's just give an example. 25 degrees C, you change that to Kelvin, what is it? 298, isn't it? 25 degrees C. So let's put another temperature, 300 degrees C. You change that into Kelvin, that will be 573 Kelvin. Get the difference between these two? Get the difference between that two. Is it going to be the same? 300 minus 25. That will be 275 degrees C. Now get the difference in Kelvin now. 573 minus 298. Isn't that 275 Kelvin? So whether you're using degree C or Kelvin, you still get the same answer. So that's why whenever it doesn't matter whether the unit is in Kelvin, or whether the unit is in degree C. CP or CV is still the same thing. Does that answer your question?
Yes, Doctor. Thank you.
Good. Okay, good. So now we have done that example. Let's look at. We did this example for exam last week. Somebody asked me. Now I just want to remind you guys. This is all about the polynomial equation. There's that 10 to the power of 3, 10 to the power of 5, 10 to the power of 8, 10 to the power of 12. Okay? So whenever you have a polynomial equation which is in this form, Cp is equal to A plus Bt plus Ct to the power of 2 plus Dt to the power of 3, you only need that A, you only need the B, and you only need the C of that, the value of C, and you only need the value of D. But what is given is the whole thing times 10 to the power of 3. So what you have, let's look at one value. For example, this value, that value, okay? So A is equals to, if I bring this up, A times 10 to the power of 3 is equals to 94.140. But you only need the value of A. You don't need A times 10 to the power of 3. So what you have to do is bring this over to the other side. So A is equal to 94.140 times 10 to the power of negative 3. You do the same thing for B, C, and D. Okay, I got a few questions last week about this. So please remember, whenever you write it inside your CP, you are actually writing the value of A, B, C, and D. So you have to times 10 to the power of negative, not times 10 to the power of positive. Okay, please, I need to remind you guys about that. Okay, this is one example. We did this. Okay, a change in temperature and pressure. We did this using the hypothetical path. We have done this, I think. We have done this, didn't it? We have covered 8.31. Okay, so now we're going to look at 8.32. So I'm going to use my 8.32. Okay. We're going to do this. We have two parts to this example. We're going to assume for our nitrogen and ideal gas behavior, we need to calculate the heat that is going to be transferred. Okay, now for part A, you have a flow rate of 100 mole per minute going from 20 degrees C to 100 degrees C. So before you start your solution, the first thing you need to do is draw your diagram. Okay? For first part, we have our diagram here. Draw your diagram, your block diagram. Coming in, it says you have nitrogen having a flow rate of 100 mole per minute of nitrogen gas at 20 degrees C. Coming out at 100 degrees C. Okay, automatically, since there's only an inlet and outlet stream, your outlet stream will also have the same molar flow rate as the inlet. So you don't need really to solve the material balance. That's automatic because in equals to out. Basis, guys. What is the basis? Anybody?
100 mole.
100 mole per minute of nitrogen gas. Please write down the gas. Okay, you can write down the gas. 100 mole per minute. Okay, now let's go back to the procedure. I need to show you that's the procedure. Okay. Perform all the required material balance. The first part, we have done that. It's automatically input equals to output. Your basis, please write your basis. Write your basis. Second part, write the appropriate equation, the full general equation. We are looking at open system. So we have the open system equation. Just now I was looking at this. Okay, so the full equation is delta H plus delta E, our kinetic energy, delta E potential energy equals to work shaft plus our heat. Okay, that's our full energy equation because this is an open system. That's your equation. Okay, what you need to do next is, since this problem is, there's no mention about any velocity, there's no mention about a change of elevation, so cancel that off, and there's no mention at all about pump or turbine, so that cancel off. So give it a reason. Your change in kinetic energy is equal to 0. Why? Because no change in velocity. Give it a reason. You need to do that, or else you will lose some marks there. Your potential energy is equal to 0. No change in elevation. Write that down. If you forgot to do this, you will lose some marks. Your work shaft equals to 0. No moving parts or no turbines, no moving parts. That's right, no moving parts. Okay, done. Yeah. Next, the question asks for heat transfer. So your heat transfer according to this equation will be the change in the enthalpy. And change in enthalpy, if you remember, we have been doing this in chapter 7. Out your mass flow rate times by the specific enthalpy minus in your molar flow rate times by its specific enthalpy. Okay. Now, we are just looking at nitrogen gas. Okay, now let's go back to the procedure. If I can go back to the procedure. Oops. Where is the procedure? Okay. The procedure said that you need a reference state. You need to specify your reference state. Okay, let's go back to our example. What reference state are you going to use, guys? What is your reference state? What is your reference state? Anybody? Anybody? Nobody? Okay. The reference state, if you look at the procedure just now, the reference state can be your outlet or your inlet if you don't have any data available. No data from the appendix and nothing, then it could be either the inlet or the outlet. So now let's go back. Yeah. Do we have any data available for this system? Anybody? Anybody? No? You sure?
Only temperature.
Data. Head enthalpy. The data, enthalpy. Is there any data available? Okay, I'm going to unshare this. I'm going to show you guys the appendix. Yeah? Now, I'm going to share you guys the appendix. Let me see. Anybody? Where's the appendix? Okay. Is this appendix? This is appendix table B8. Have a look at it. Where is nitrogen? Is there nitrogen?
Yes.
There is nitrogen, isn't it? There is nitrogen.
After oxygen.
Yeah, there is nitrogen. Okay, let's look at nitrogen. This is nitrogen. I cannot scribble. Let me try to scribble. Okay, that's nitrogen. Okay, what temperature is the question at? 20. There's no 20 here. There's only 20. There's 100. You have 100. There is 100. Let me use this. There is 100. This is nitrogen. This is nitrogen. Okay, your value, the enthalpy at 100 is equals to 2.19. The unit is in kilojoules per mole. The reference state is stated here. This is your reference state. So the value of the enthalpy in the appendix, which is table B8. But if, for example, you don't have it, just say that you don't have it, then you need to specify your reference state. But if you have it available, you need to follow the same reference state as that in the table, which is, for this case, 1 atm 25 degrees C, nitrogen gas. You need to specify that, the same reference state as that of where you get your data from. Okay? So let's do this both ways, having the data and without having the data. So let's say now we are going to use this table. So my reference state should be the same as that table. So let me get the value now. At 100, I need to integrate actually. Okay, so I'm going to go back to my, I'm going to unshare this because I need to show you guys my iPad in order to do the calculation. Okay, it takes some time. I don't know why it's not. Okay, there you go. Now let's look at the data that we have. When it is at 0, it is temperature, degrees C, and this is your specific enthalpy. The unit is kilojoules per mole. If you have any question, please ask, because I don't know whether you understand or you don't understand. So the first temperature we have is 20. That's the inlet. The outlet temperature is 100. And the one that is next to 20 is 0. The value of the specific enthalpy for nitrogen at 0 is minus 0.73. If you look at table B8, and the value at 100 just now, I did mention to you guys, the value at 100 just now is equals to 2.19. Now, if you're going to use the table B8 from the appendix, then your reference state should be the same as that appendix, so as that table. So your reference state is going to be nitrogen gas. Specify the phase. You need to write down. Do not say gas. It's wrong. It could be any gas. What gas? Specify. It is nitrogen gas. What temperature? 25 degrees C. What pressure? 1 atm. Okay? Because when I look at your assignment, some of you just specified gas. It could be any gases. You have to be very specific. What gas are you dealing with? So you need to specify that gas. In this case, it's nitrogen. So what is that value for enthalpy 1? This is enthalpy 1 or in. Okay, let's give it as 1. This is enthalpy out, specific enthalpy out. That equals to 2. Okay, so what is enthalpy 1? After you have interpolate, guys, give me a value. It should be negative. Why did I say it's negative? Because your reference state is at 25. When it's 25, the enthalpy is 0. But 20 is less than 25. So it will be negative. What is that value, please? Anybody? Do I need to do it myself? Give me a value, please. Okay. Nobody is going to give me a value.
Minus 0.146.
0.146. Negative, isn't it?
Not sure, yeah.
Okay, thank you very much, Muhammad Faizal. So now, that is your enthalpy at the inlet. So if you do it using this equation, if you put that value, equals to your outlet, the mole is the same, inlet and outlet is the same, so you can take out that molar flow rate. So it will be H out minus H in. Because the molar flow rate is the same. So you're going to do 100 mole per minute. H out is equals to your enthalpy out is at 100. That's the temperature, so 219 minus. Okay, I need a space. I need space. I need to undo that. Yep, I need to bring it over to this side. Equals to 100 mole per minute. Your H out just now is at 100 degrees C, so this is equal to 2.19. What's the unit? The unit is in kilojoules per mole. And that we just got it from interpolation minus 0.146. So putting in these values inside this equation, you will be able to solve for the heat flow that is being transferred or being removed from the the unit. That's minus 0.146. What's the unit is kilojoules per mole. Oops, I'm not going to do that. I'm going to write it, okay, per mole. So cancel the mole. Your answer will be in kilojoules per minute. So if you do that, what's your answer? 100 times 2.19 plus 0.146, you will end up with 233.6 kilojoules per minute. What is the answer from inside the textbook? Example 832. If we look at the solution, not the solution 832, the answer is 233 kilojoules per minute. We get 233.6 kilojoules per minute. Okay, that's one method when you have your data available. Now I'm going to do it differently when you don't have the data available. Did anybody, all of you manage to get the same answer? Any questions?
Yes, Doctor. Same answer.
Good. Any questions?
No
Okay, now
question.
I'm going to do it differently. I'm going to assume that I don't have any data available. I'm going to assume that I don't have any data available. So let me redraw this. I have 100 coming in, 100 mole per minute of nitrogen gas at a temperature of 20 degrees C, coming out at 100 degrees C, the same mole per minute of nitrogen gas. So now my basis, I already said I'm going to use the same basis, so it should be no problem. My reference state, now my reference state is not going to be the same as any table because I don't have any table to refer to. I'm assuming that I don't have any available data available and I cannot get it anywhere directly from any sources. So I have to use my own reference state. I can choose any reference state I prefer. So let's say my reference state is going to be my inlet condition. So it's going to be nitrogen gas. Specify your component. What state is it? Gas, solid, liquid? Okay, gas. My temperature is the inlet temperature. And I'm going to assume that since no pressure is given, I'm going to assume that it is at 1 atm. Okay, so that is my reference state. So if that is my reference state, so my specific enthalpy at that inlet condition is going to be 0. Now I need to find my outlet enthalpy because I do not have any value for it because it's not my reference state. So I need to find it. So if I want to find that value, I'm going to need some sort of maybe polynomial equation to integrate. In this case, definitely there's a change of temperature from 20 to 100 degrees C. There's a change of temperature. So if you go back to our, let me see, to our equation for the table just now. I'm going back to the table. I'm just refreshing you guys on the fact that when there's a change in temperature, you only need to integrate, okay? Now, this is the table. We're looking at ideal gas. Why are we assuming ideal gas? Because the temperature is 20 and 100. The temperature is not in the negative. The pressure is 1 atm. We assume it's going to be 1 atm, even though it's not specified. So the pressure is not high. It's just 1 atm. So the enthalpy change will be the integration of Cp with respect to temperature. So that is how you're going to get your enthalpy. So let's go back to our example. Okay. So in order to get H2, I need to use black color. So let's do that. So your enthalpy 2 actually is delta H, which is minus enthalpy 1, but enthalpy 1 is equal to 0. So that becomes your specific enthalpy 2, which is the outlet. This is equal to outlet. Okay. This is in. So integrate from your reference state. Where do you start from? 20 degrees C. Your final temperature, 100 degrees C. And your CP with respect to temperature. So in order to get that CP, you need to look it up in appendix B2. So we are looking at nitrogen. So let's look at our appendix. I'm going to stop sharing this. I'm going to show you guys the appendix. And let's share. Let's look at the appendix. Okay, where is B2? That's B8. This is B5. That's B1. We don't need B1. We need B2. So that's B1. That's B2. We are looking at nitrogen. So the component, they are arranged alphabetically. So let's look for N. Where is nitrogen? Okay, the top component listed here is nitrogen. So I'm going to, let's see. I'm going to use this to show you guys. We are looking at nitrogen. That's nitrogen. Oh dear. Let me, oh dear. That is your nitrogen. Okay, your polynomial equation. Okay, that's your polynomial equation. Anyway, I can undo that. Oops. Sorry guys, I need to do that all over again. Somehow, I'm not very good here, and I'm not very good using this. Okay, there you go. That's nitrogen. Okay, your equation is going to be equation 1. Okay, your equation is going to be equation 1. That's 1. Okay, you are looking at gas. That is gas, nitrogen gas. That is your A. Where are you? That is your A. Not your A actually. A times 10 power of 3. That is your B times 10 power of 5. That is your C times 10 power of 8. And that is your D times 10 power of 12. Okay, you are looking at gas. You're using equation number 1. So let's write down the equation. CP. I'm going to go to my iPad. I'm going to stop this. And let's look at my iPad. Okay, this is it will take some time. Somehow the internet is not that fast. Okay, good. Okay, let's look at let's write down our CP. A plus BT plus CT to power 2 plus DT to power 3. And if you look it up in appendix B2, your A is 29 for nitrogen gas. Okay, times 10 to the power of negative 3. Please remember the negative 3. And your B is 0.2199. 0.2199 times 10 to the power of negative 5. T, that's the T temperature. C from that appendix is going to be 0.5723 times 10 to the power of negative 8. T to the power of 2. And lastly, your D from that appendix B2 is negative 2.871 times 10 to the power of negative 12. T to the power of 3. And this CP, the unit is in, what is the unit, guys? If you look at the appendix, what is the unit? Unit is kilojoules per mole. Kilojoules per mole degree C or Kelvin. It's the same thing. Okay. Okay, now that is your CP, so you need to integrate. So your delta H out is equal to H2 specific is equal to from 20 degrees C to 100 degrees C. You write it down your polynomial equation. I'm going to repeat it all over again. Yeah. T to the power of 2 minus 2.871 times 10 power minus 12 T to the power of 3 with respect to temperature. So once you have done that, so what is your answer, guys? What is your answer? Integrate because you do have the calculator that you can use. You need to know how to do that. What is your answer? If I look at the textbook, let me have a look at the textbook. The answer given is 2.332.
Yes, it's the same.
Thank you. Kilojoules per mole. Now you don't have the temperature term there anymore because you already cancelled it out. That is your same. Thank you very much. 2.332. So that is your specific enthalpy out. So now based on the equation that we got earlier, that's the change of out molar flow rate, specific enthalpy out in molar flow rate, specific enthalpy. So if you do this, all you have to do is take out the molar flow rate because it's the same in and out. So that's don't have the summation now. It's H out minus H in. Okay, so your molar flow rate, I need a bigger space than that. So I'm going to write it over here. Again, the same thing, mole per minute. Okay, your H out is the one that we just got just now, which is that value. 2.332. And what is the value of your specific enthalpy for the inlet, guys? What is the specific enthalpy of your inlet?
0, doctor.
0, because that is at your reference state. Okay, thank you. So that is kilojoules per mole. Okay, that's the answer. Kilojoules per mole. Cancel off the mole. Will end up with kilojoules per minute. So automatically this is 2.332 times by 100. It becomes 233.2. That's your answer if you use the integration, how to solve it using integration. That's 233.2. If we use the data, we got that value, 233.6. That's very close. It's almost the same, 233.6 and 233.2. The only difference now is because the first part you use appendix B8. You're using appendix table, appendix B8. Because it's available, why not use it? But if you don't have any data available, then you have to use the integration in order to solve for the change in temperature. Any question, guys? Any questions?
No question, doctor.
Thank you. But now I need to point out your reference state. If you take note of both solution, your reference state is not going to be the same. Your reference state for the first solution has to be based on where you get your data from. The second solution, because you don't have any source of data, then you can either choose the inlet or the outlet. It's a matter of choice. Which condition do you want to be your reference state? It's just a matter of choice. Make sure that your reference state must have every data available. The state of the component, the temperature, and the pressure. Okay, so that's done. For the second part of this example, I got the whole thing over here actually. The second part of this example is nitrogen gas in a 5-liter flask at 3 bar, initial temperature at 3 bar, being cooled down from 90 to 30 degrees C. Okay, for this example, you are looking at a constant volume. This is a constant volume. It's a constant volume, and it is a closed system. That's the difference between the first problem and this question. From the first question and the second question. This is a closed system, so you need to find what you need, Q. Okay, now let's do this. Let's write down for the second part. You have a closed system, and that's another thing I need to point out. When you have a closed system, do not draw a block diagram where you have inlet and outlet. It's closed. There's no inlet, there's no outlet. Okay, what do we have here? We have nitrogen gas at 5-liter pressure 3 bar. Yeah, I need to go up and down here, scroll up and down. Initial pressure 3 bar. We have a volume of 5 liter. The volume will be same, constant. Your pressure too, you don't know. Yeah. And what else is specified? Temperature 90 and 30. The initial temperature is 90. T1 equals to 90 degrees C. The final temperature is going to be 30 degrees C. Just put it that. Okay. Obviously, you are going to take out heat. You're going to take out the heat. Why? Because the temperature is going down from 90 to 30. Okay, now how to solve this problem? You know, it's a close your basis. What basis are you going to use? That will depend on, let's see, 5 liter. You have the liter. 5 liter of what? You have nitrogen gas. Or 5 liter of nitrogen gas. That's nitrogen gas. Okay, so that's your basis. Reference state. Reference state, you can choose either one of it, inlet or outlet. You can do this problem using appendix B8, of course. Why? Anybody? Can you answer? Why can, I mean, you can still use appendix B8, table B8. Any reason? Anybody?
Because in table B8 there is nitrogen gas.
Sorry, Arif?
Because in the table B8 there is nitrogen gas.
I don't know why I can't hear you. Somehow. Okay. Can you repeat that again?
Because in table B8 there is nitrogen gas data.
Okay, but then look at the table. The table state that the pressure is 1 atm. Our pressure is 3 bar. It's the approximately 3 atm. Can you still use that table?
Because CV independent of pressure. CV.
Okay, sorry, can you repeat that again, Ibrahim?
It's CV and CP only function in temperature, so it doesn't matter.
Okay, not really CP and CV. Ideal gas doesn't depend on pressure. Ideal gas, only ideal gas. The change in pressure doesn't affect the enthalpy and the internal energy. I did mention that this at the very beginning of this lecture. The internal energy and the enthalpy is not affected by the change in pressure when you are looking at ideal gas. So now you have to state down, assume ideal gas. You need to assume ideal gas. You can do that because your temperature is above negative. Your pressure is not that high. It's about 3 atm. It's not that high. So you can assume ideal gas. So when you assume ideal gas, then the change in pressure is not affecting the enthalpy change, and neither will it affect the internal energy change. Okay, so you still can use appendix B8. But I'm not going to do appendix B8 right now. I'm going to use the same method as the textbook. You can do the same, you can use appendix B8. You can check whether our solution is going to be the same. You can do that. Huh? Let's do this. Your reference state, let's say, because you have every information in the initial condition, so we're going to use temperature 90 degrees C as the reference state. First thing, note down the gas, nitrogen gas, and the pressure is 3 bar. So that is your reference state. Okay, that's your initial state. So now that condition will give you enthalpy of 0 and your internal energy equals to 0. Okay, so now what do we have? We're going to assume that we don't have any data available. So we're going to use the enthalpy from the appendix it's the CP, sorry. We're going to use the CP from appendix B2. So this is your CP. From appendix B2, that is your CP. We're going to use that, and we're going to use this equation. We need actually write down the equation for closed system first before you start anything else. Delta U, internal energy, delta E for kinetic energy, and potential energy is equals to heat plus work. So cancel the drop off some terms over here. Give reason. I'm not going to write it down. Please state the reason why you drop it off. And then I'm going to have this final equation. The change in internal energy, and that's going to be initial, not initial, it's going to be final, which is the change in the mass, and that's specific. I'm not sure whether the molar amount. There should not be any dot there because it's not flow rate. Let's write it again. Okay, and that's initial. It's not the same as in and out because you don't have any flow rate. Please do not write the block diagram with having inlet and outlet. I noticed that in your assignment. Yeah, that's wrong. So now, calculate the amount of mole. So you have volume equals to 5 liter. The initial condition. Okay, the initial condition, you are given the temperature is equals to 90 degrees C. Your pressure is 3 bar. So you're going to find using PV equals to nRT, which is the ideal gas law. N equals to PV divided by RT, and your pressure is 3 bar. Your volume is 5 liter. Your gas constant, we're going to write that later on. What is your temperature? 90 plus 273. Change that into Kelvin. So what is your gas constant? Let's look at the gas constant that we're going to use. First thing first, take note of the unit, liter and bar. Now I'm going to scroll up until I find the gas constant. Okay, we have liter over here. We have, but the unit is the pressure is in ATM. This is liter, but the pressure is millimeter mercury. I'm not going to use that. Okay, there's another here, liter and bar. So we're going to use this. Right? That is our gas constant that we're going to use, 0.08314. So let's go back to our solution. 0.08314. The unit is going to be, okay, I think I got it. I wrote it wrongly. Should be in the denominator. 0.08314. That's liter, bar, and Kelvin. And what else? What is it? Is it mole? Is it mole? Mole. Okay, it's mole. Mole. Okay, cancel the Kelvin, cancel the liter, cancel the bar. You end up with its mole. What's the answer? Let me calculate 3 times by 5 divided by 90 plus 273 divided by 0.08314. I managed to get 0.497 mole. Let's see, what is the answer in the solution? Oh, there's no answer in the solution. Yes, it's the same, 0.497. Did you guys get the same value? Same as the solution. I managed to get the same as the solution in the textbook. Anybody? Check my calculation?
Got the same answer.
Yes, good, thank you. Now, you get that number of mole. So if you go back to the equation just now, Q is equals to the change in internal energy. Bring out the number of mole. Why? Because the number of mole is the same. Whether it's in the initial state and the final state is still the same. Nothing changed because you do not add in any nitrogen into the system. Neither do you take any nitrogen out from the system. It's a closed system. So your amount of mole is going to be constant. So that is going to be out. Final is not out. There's no out. Nothing coming out. Nothing coming in. So it's initial. This is going to be your equation that you're going to use. Let me highlight that. That is the equation that you're going to use. Yeah. So let's solve for your final. What is your initial U? What is your initial specific internal energy? Guys?
0.
0. Why?
Because it is our reference state.
Yeah, thank you very much. Yeah, because it's your reference state. Now you need to find your final internal energy. Yeah. So the fact that we already have CP, you know you're going to use CP. is equal to CV plus U. Sorry. What should it be? Gas constant, isn't it? Right? U is equals to the integration CV dt. And where you assume your reference state, that is where you start at 90 degrees C, and your final state is at 30 degrees C. 30 degrees C. Okay, so your CV, you need to find your CV. CV equals to CP minus R. Okay, the first example we did just now, we have something like this, similar to this. Now, let's go back to your CP. That's your CP. What R are we going to use? Your unit is kilojoules per mole per degree C. So what R are we going to use? Minus what? Let's look at our gas constant having kilojoules per mole per degree C. Let's look at our gas constant. Okay, I'm going to erase this because I'm not going to use that. Okay. Okay. So let's look at any gas constant that have kilojoules per mole degree C. The closest that I can find here that have joules is this. That's the value. Now I need to change it to kilojoules. So if I'm going to change it to kilojoules, let's do the calculation. 10 to the power of 3 joules equals to 1 kilojoules. Cancel your joules. You will have divide by 10 to the power negative. You got the negative divided by 1000. Now you need to change it to kilojoules per mole per Kelvin. Why? Because the equation that we have earlier from our CP, that is in kilojoules per mole per degree C. So that will be, let's look at my gas constant just now. 8.314 times 10 to the power negative 3 minus 8.314 times 10 to the power negative 3. You have that term, negative 3. You have that term, negative 3. Right? So this is not CP. This is equals to CV equals to minus R. What I'm doing now is CV equals to CP minus R. So if you take 29 minus 8.314, I'm calculating that value. So I will end up having this C value is equals to, my CV is equals to 20.686 times 10 to the power negative 3. Okay, what I'm doing now is actually I'm deducting 8.314 from 29. Okay? Deduct 8.314 from 29, you get 20.686 times 10 to the power negative 3. So that's 20.686 times 10 power plus times 10 power negative 3, and repeat the whole thing all over again. 0.2199. I'm going to scroll up and down. Sorry guys, but I need to scroll up. Times 10 minus 5 T, and let me see whether I can get it faster without scrolling up and down. I'm sorry, I do need to scroll up and down. 0.5723. 0.5723 times 10 power of negative 8 T to the power of 2 minus, I'm looking at this equation now, 2.871 minus 2.871 times 10 to the power minus 12 T to the power of 3. So that is my CV. So putting in that part of the equation, all these values over here with respect to time, what is the answer, please? This will be your final internal energy. So do the integration using your calculator. What is the answer, please? Will you get the same as the solution? Let me see. The solution, no, they do not give the answer for that part. But give me an answer, somebody. I also will calculate it. Let's do it. Okay, 20.686 times 10 to the negative 3 plus 0.2199 exponential minus 5 alpha x, because that's your T, plus 0.57 2, 3 exponential minus 8 and alpha x square minus 2.871 exponential minus 12 and alpha x to the power of 3 comma the temperature change is from 90 comma to 30 close equals, the answer is equal to negative 1.2504. Did you get that, guys? Anybody? Did you get that, or did I wrongly calculate? Please check my integration.
Same answer.
Same answer.
Yes.
2504. Sorry, I should. Good. Did you get the same? Okay, that's the integration. So that's your final U. So now, going back to this equation. So your Q is equal to the number of mole. This now we calculated. That's the number of mole. 0.497. That's mole. There's no minutes here. So U final, we just got minus 1.2504. And your U initial is minus 0. So if you calculate, the unit is going to be in, what's the unit, guys? Your U, what's the unit? Look at your CP just now. What unit do you have? Kilojoules per mole. So that's kilojoules. Kilojoules per mole. So cancel the mole, you will get your answer in kilojoules. So what is the answer, please? It's negative. So Z times 0.497, you will get negative 0.6214. Did you get that?
Yes, Dr. Sam.
Good. So that's your answer for the second part of that example. And if you look at the solution from the textbook, the solution given in the textbook is negative 0.621. Very close. Exactly, actually, 0.621. We got 0.6214. We are 4 decimal places. The textbook is 3 decimal places. Any question? And see whether if you do this problem, the second part, using the text appendix B8, you have to remember this equation. H equals to U plus PV. That's a bit complicated, but you can solve. U equals to H minus PV. It would be better off if you use the integration. That's easier. But then that's not a problem if you want to solve using the appendix B8. But it's easier if you use the integration. Any question, guys? What's the time? It's 9:30. Okay, still have some time left. Any question, guys?
No question.
No question. Thank you. So let's look at our notes again. We have done this. Let's scroll up. We did this now. Example 832. We did this. Yeah. Now let's look at example 833. Okay, this is one example where you have 15 kilomole per minute of A. Okay, when I look at A, I will know I will use appendix B8. Yeah, because I have A there. It's cooled from 430 degrees C to 100 degrees C. I can assume I did gas because the temperature is above negative. There's no mention about pressure, so I'm going to assume it's going to be 1 atm. The question asks for heat that need to be removed when you cool it down from 430 to 100 degrees C. The first step, use this appendix. The first step, use a table B2. That means you need to integrate. The second step, use appendix B8. This example is similar to the previous example, actually. Okay, so let's look at for A. So we have A over here. This is A, the molecular weight of A. Gas. Your equation is the first form. This is your A, that's your B, that's your C, that's your D. You're going to use this equation. That's it. Okay, now I need to point out. Just now somebody asked, why is it the same? This is degree C, this is degree Kelvin. It's the same because there's the temperature different. Okay? The unit is going to be the same. It's going to be the same. Okay, that's we are going to solve it using the first equation, the first table B2. the second part of it using table B8. So let's look at table B8 first because that's the easiest one. This is example 833. Where is 833? Let me see. Where is my 833? Okay, there. Yeah. We have A coming in because you have that per minute flow rate. So you need to draw your diagram. You draw your diagram. Inlet coming in, outlet going out. Okay, 15 kilomole per minute. Kilomole per minute of A. Yeah, the same outlet flow rate because there's no other stream coming in and out, just the two of them in and out. There's only one in, there's only one outlet. So it's cooled down from 430 degrees C going to 100 degrees C. So if we're going to use appendix table basis first, guys, don't forget the basis. Your basis, okay, that's the flow rate, 15 kilomole per minute of A, inlet. Your reference state, since we're going to use appendix B8, we're going to use the same reference state. So our reference state is going to be this reference state. The same, but specified that you are looking at gas A. It's A bracket gas. The temperature 25 degrees C, the pressure 1 atm. That is the same as appendix B8. Yeah. So next, since that is your reference state, look at the table. We have at 430, well, we don't have 430, we have 400, we have 500. So you need to interpolate between 400 and 500, that temperature. That's your temperature. This is your in specific enthalpy in. This is your specific enthalpy out. The specific enthalpy out, that's no problem because you have it exactly at 100. That's 100, and so that's the value. Now you need to interpolate between these two values. Yeah. Try to get that, guys. What is that value over here at 430? Try to give me that value, please, for the enthalpy out at 430. At this temperature, what is your enthalpy? Oops, I better not do that. Okay. If I have to write it down, this will be how it look like. Temperature, degrees C, specific enthalpy. What is the unit of my specific enthalpy? Kilojoules per mole. Please make it a habit of writing down the unit because whenever you need to double check, you will know what unit you need to refer to. 400, 430, 500. Okay, 400, the value is 11.24. And at 500, the value is 14.37. So what is H out? Anybody give me a value? Should be somewhere 12 something, maybe?
12.18.
Sorry, 12 point? Oh, can you repeat that again, please? 12 point?
18, Doctor.
8.
18. 12.
18. 18. Okay, 18. Thank you. 18. Okay, 12.18. So that's done. 12.18. That's easy. And what? Sorry, that's not not there. 12.18 is the inlet, not here, not the outlet. Okay, now the outlet just now we say is 100 degrees C. That value is you can read it directly from the table, 2.19. The unit kilojoules per mole, just like I said just now, please write down the unit. Do not skip the unit. So now, this is an open system, write down the equation, the full general equation, please. You need to write down the full general equation. Do not skip some of the terms because you're going to need to write down the reason why you drop it off. Okay, that's the full equation. Cancel the kinetic, potential, and work shaft. Give the reason. I'm not going to write it down because I have shown you guys how to write it down. So now we know that the heat that need to be removed is the change in the specific enthalpy. Sorry, the change in the enthalpy, the rate of enthalpy change. That is going to be out. And specific enthalpy, molar flow rate, 1 atm time by specific enthalpy. Molar flow rate time by specific enthalpy. So since we have only one stream coming in, one stream going out, take out the molar flow rate. It will be just a specific enthalpy out minus specific enthalpy in. And since we already have both values, so we're going to write down the values that we have for out is 2.19. Sorry, write down the molar flow rate first. I seem to be rushing now. 15 kilomole per minute. Our outlet value of specific enthalpy minus our inlet value 12.87, which we got when we interpolate just now. That's kilojoules per mole, but the unit is kilomole, so change it to kilomole. 10 to the power of 3 mole equals to 1 kilomole. Okay. So you have kilomole, cancel kilomole. Your answer will be in kilojoules per minute. And what is the answer, guys? Let's have a look at the solution. It's minus. Okay, the textbook give it in kilowatt, so we need to change it to kilowatt. Okay, let me undo this. Put it in kilowatt per minute. 1 minute 60 seconds. And it will be in kilowatt. So what's the answer? Let me do the calculation since nobody is going to respond. After I've done it, then you can check whether I did whether my answer is the same as yours. That's going to be negative 160,200. So I divide that by 60. I hope I get it the same as you guys. Negative 2.670 kilowatt. What is the solution from inside the textbook? Oh, what did I get? Sorry, it's 2,000. 2,670. The textbook, the answer is 2,500. Did you get the same as me or did you get the same as the textbook? Anybody?
As you teacher.
As me. Thank you very much. Muhammad Ikmal, is it? Is it Muhammad Hakim? It was too fast. I cannot see your. I'm not sure who it was. So the textbook got it wrong. The textbook got it negative 2,500 kilowatt. We managed to get to negative 2,670. Negative, why? Because you're getting out. The heat is coming out from the system as you are cooling the A from 430 to 100 degrees C. You are cooling it down. So the heat is being removed. That's why the negative sign. So that's solved. That's the second part of the problem. Now let's do the first part. You're going to use table B2. So that's table B2, that's B2. You're going to look at A, that's A, is gas. The first equation, so this is the first equation, so you're going to use that equation. That is your value for A times 10 to the power of 3, B times 10 to the power of 5, C times 10 to the power of 8, D times 10 to the power of 12. So if you're going to write that down, CP, oops, I should not do that. Use my pencil. CP is equals to 28.94 times 10 to the power of negative 3 plus 0.4147 times 10 to the power of negative 5 plus 0.3191 times 10 to the power of negative 8 minus 1.965 times 10 to the power of negative 12. So that is the value that I get from my polynomial equation over here. Huh? Yeah, you guys can see it. That's exactly. The only difference is that I have the times 10 power negative there. Yeah, that's my CP. And now, let's solve this problem. We're going to have our basis still the same. Nothing changed. The basis is still the same. The reference state will be different. My reference state. What should be my reference state, guys? Anybody? What reference state? Anybody? Sanjay, you just joined in. We are almost done. Anybody? What is the reference state? When I'm using the polynomial equation. Anybody? Nobody going to respond? Guys?
Doctor, the inlet or the outlet stream?
Okay, which one do you prefer?
The
Omar?
inlet.
Inlet or outlet?
Yes.
Inlet.
Inlet. Yeah.
Okay, inlet. So the inlet is 430 degrees C. So write down A, gas, 430 degrees C. You're going to assume it's going to be at 180 M because there's no mention at all about the pressure. So that is your inlet condition. So if that is your inlet condition, so now I'm going to erase this because we are no longer using that value anymore. We're not going to use that value anymore. We're going to use a different value for enthalpy because we do have a different reference state. So that's going to be 0. Now, what is that outlet and specific enthalpy? So that's what we need to do. So let's write down, we already have the equation just now. That is the equation. Yeah, we're going to use the same equation. Nothing changed there. We just need to find the outlet enthalpy. Outlet enthalpy equals to delta H out minus delta H in. But your inlet is now at this is your inlet condition. So that is going to be 0. So that is going to be H out. And H out, if you use the polynomial equation, because there's a change of temperature, just a change of temperature from 330 to 100, there's a change of temperature. So there's no change in pressure. So you will just be looking at the integration from the initial condition. Well, initial condition is 430 and your final condition is 100. You're going to integrate that with respect to temperature. So just now I already wrote down the CP. That's my CP. Let me highlight it. That is my CP. So I'm going to write that down in my integration. 430, 100 degrees C. Okay, I'm going to scroll up. Sorry about that because I can't remember. 28.94 times 10 to the power negative 3, bracket it, plus 0.4147 times 10 to the power negative 5. Next, 0.3191 times 10 to the power negative 8. Oh, guys, please remember your t square. Do not forget that. And lastly, minus 1.965 times 10 to the power negative 12, t to the power of 3. Close the bracket, dt. So now, what's the answer? When you do the integration, I'm also going to do it using my calculator. This is going to be quite some time. Let's do it. Integration 28.94 exponential minus 3 plus 0.4147. You better do it together with me because you need to be familiar with doing integration. Alpha x, where is my x? Okay, plus 0.3191 exponential minus 8 alpha x to the square minus 1.965 exponential minus 12 alpha x now is to the power of 3 comma from a temperature of 430 comma to a temperature of 100, close the bracket, equals to, I managed to get minus 9.9796. What is the unit? Let's have a look at the unit. Kilojoules per mole. Did you guys manage to get the same value?
Same, doctor.
Thank you very much. Okay. That is your H out. So write that down. H out equals to minus 9.9796 minus 9.9796 kilojoules per mole. Please write down the unit kilojoules per mole. I almost forgot that. So now, just putting in the value inside this equation. Let me highlight that inside this equation. Just putting in that value. So let's write that down. Q is equals to N out minus in Your amount of flow rate just now is 15 kilomole per minute. I'm going to write it down over here. I'm going to change the unit till I get kilowatt. 1 minute, 60 seconds, because I need it to be in kilowatt. Okay, the out value that we just got just now is minus 9.9796 minus 0, because your inlet is your reference state. The unit is kilojoules per mole. Again, you need to change it to kilomole. So 10 to the power of 3 mole equals to 1 kilomole. So cancel off mole, cancel off kilomole. Your answer will be kilojoules per minute. That is, per second. That is kilowatt. So let's calculate. 15 times negative 9.9796 divide times 10 to the power of 3 divided by 60, you will get negative 2,449. 9.9. Did you manage to get that, guys? 2,495, roughly. Anybody get a different value? Calculate, please. Check my calculation. I might be wrong. Did you get minus 2,495 kilojoules per second?
Same answer, Doctor.
Thank you very much. So that's your answer for the first part using integration. Let's check. This is 2,494.9. The previous one is 2,670. That's a great.
Doctor,
Yes.
for the first part,
Mm-hmm.
it's actually 2,500 because you used 12.87 instead of 12.18.
Okay, guys. Somebody pointed out it should be 12.
Actually, it was pointed also in the chat.
Yeah, 12.18, isn't it?
Yeah.
Yeah, sorry guys, I make mistake there. It should be 12.18. Should be 12.18. It should be, let me. Okay, thank you very much. Somebody somehow, I don't know why I brought 12.87. So let's erase that. Yeah, let's erase that. And oops, why can't I erase it? Okay, right. It should be 12.18. Thank you. And so our answer should be the same, isn't it? Should be negative 2,500, is it? Check, please. I made a mistake there. Sorry, guys. This is how you make careless mistakes. I don't know
Yes.
what happened. Yes, thank you very much.
Yes, it appeared to be around 2,500.
2,000 what? Mama,
It's actually 2,497, so 2,500.
okay. 2,400. Let's write down 2,497, is it?
Mm.
Thank you, Faizal. Muhammad Faizal. Thank you. So that's quite close to what we got for the second part. 2,495, 2,497. Negative because you're going to take out heat. So that's why the negative sign. So guys, any questions so far? We have looked at 2 examples that involve only heating and cooling. This is cooling. The previous example, 832 was heating, if I'm not mistaken. We heat it up. Yeah, we heat it up. This is heating. We heat it up. Just now the example that we did, 3833 is cooling. Just heating and cooling. No change of pressure. No change of, well, if there is a change of pressure because we are using ideal gas, it will not affect it at all. And no change of phase. There's nothing changing from gas to liquid or liquid to gas. There's no change of phase. So it's just simple integration. So any questions? Any questions? Anybody?
Clear, Doctor.
Clear. Thank you very much. So if that's clear, so we will continue with more examples tomorrow. Okay, I need to unshare this because you need to scan the QR code. Just now I was having problem showing you guys the QR code. I don't know why. Let's see, where is my QR code? Oh dear, what happened? I did not have it here. Let me get to my QR code. I did it just now. Somehow when I get out of this, I unlock my. I mean, I log out just now. Somehow I did not. I lost it. The internet is quite slow here in UTM. Okay. Okay, let's share the code. Hey guys, please scan the QR code. Thank you, Sanjay. You arrived quite late, and you're the first one to scan. Okay. The test that you have just done last week will be marked by Dr. Mahathir and Associate Professor Dr. Asnizam. So how do you find the test? Is it very difficult? Is it tricky, or is it just okay? It's okay. It's quite easy. What's your opinion, guys?
The test, doctor.
Sorry.
The test,
Yes, the test.
some question are doable, but some question undoable.
Which one is undurable?
For me, number 2.
Number 2 is.
Yeah.
Okay. Number 2 is all about what?
Uh,
Mama Ikmal?